So let's take a look at a specific example of where we can apply this idea of following the change in momentum of a system. So here we have a rocket. This is a classic application of this concept. It's a little more complicated than one I would expect you to be able to do, but it's not difficult to follow. So let's take a look and see just how useful this idea can be. So the idea is we have to choose a system and we have to be consistent about the system. All parts of the system before and after some event happens have to be the same. So imagine that we start off with a rocket that has a mass m. It's traveling with a velocity v, in this case straight up. Now as the rocket motor burns, it's expelling fuel, it's expending exhaust gases out the back end of the rocket. And so if we wait a small amount of time, delta t, and examine our system again, we'll discover that part of the system is still moving forward, but now with a velocity v plus delta v. And part of our system, the expelled rocket exhaust, is actually separated from the rocket, and that's moving with a speed v minus ve, where v sub e is the velocity of the exhaust. So the rocket is essentially broken into two pieces. The part of the rocket that is still intact, so to speak, slightly lighter, going faster, and then we have the part of the mass that's been expelled traveling in the opposite direction. So all we're going to do then is take a look at the momentum of our system before the exhaust is expelled and take a look at the very same system after the exhaust has been expelled. It's separated itself from the rocket. So the initial momentum of our system is just the mass of the rocket times its velocity. All the pieces are moving together. Afterwards, we have this. The first term is the mass of the remainder of the rocket, the original mass minus the amount that's expelled, multiplied by the new velocity of that part of the system, v plus delta v. The momentum of the other part of the system is the mass of the exhaust that's been expelled times its velocity. And so now let's actually multiply all that out to see what we get. So if you do a little bit of algebra, you can multiply it all out. We get these 6 terms. And if you look carefully, you can see that we can actually cancel out a few of them. For example, these two terms are identical. One's positive and one's negative, so they cancel out. The other term that we can get rid of is the fourth term right there. And the reason we can neglect that is because it's the product of two small changes. To a good approximation, then, what we're left with is just these 3 terms. Now we can take a look at the change in momentum of our system. So that's just final minus initial. So we take final minus initial. You can see that the mv term cancels out, and all we're left with is m times delta v minus delta me, the mass of the exhaust, multiplied by ve, the velocity of the exhaust. We want to write everything in terms of just the mass of the rocket itself. So delta m, the change in the rocket's mass, is equal to negative delta me, the change in the mass of the exhaust. So in other words, if the amount of exhaust is increasing, the mass of the rocket itself is decreasing. This is really the only subtle point. We want to write delta p for the system only in terms of the mass of the rocket. We want to get the mass of the exhaust out of there. So that leaves us with this expression then, which is strictly in terms of the mass of the rocket itself. Now if we divide through by delta t, we get this. And you'll recognize then that the things in parentheses start to look like derivatives. So if we take the limit of this expression as delta t goes to 0, and that's really the justification for ignoring that term we x'd out in blue. As we take the limit that delta t goes to 0, that term is going to vanish because it's a product of two small quantities. So if we take that limit, we now get this. So now we have dp dt, the rate of change of the momentum of the system, is equal to the mass of the rocket times dv dt of the rocket plus dm dt for the rocket times VE, the velocity of the exhaust. Now, from what we've learned before, dp dt for a system is just equal to the external force, the net external force acting on the system. And so this equation that I've highlighted in green then now describes the motion of the rocket. So if you like, you could call this the rocket equation. It's not one I'm going to ask you to remember or that we're going to use in lots of different ways, but it's an interesting result which describes the motion of a rocket. So let's take this equation and let's apply it to two different interesting situations. The first one is if there is no net external force. So this would be an example of a rocket traveling through space between the planets or even between stars where there are no significant outside forces like gravity acting on the rocket. In that case, we can write the rocket equation like this. The external force is 0. We can move the dm dt term over to the right. And so here we have an equation describing the rocket in the absence of any external forces. Now I would point out, by the way, that dv dt on the left, that's just the acceleration of the rocket. So we have m, the mass of the rocket, times the acceleration of the rocket. M times a, that's just the net force acting on the rocket itself. So notice what this tells us. It tells us that the net force acting on a rocket, just due to its thrust, is the VE, the velocity of the exhaust, times dm dt, the rate at which the rocket is expelling mass. So that's actually a really cool result. Most rocket engines, by the way, tend to expend fuel at a constant rate. So that means the thrust, which is just going to be dm dt for the rocket motor times the velocity of the exhaust, that's actually a constant force. The more rapidly the exhaust is traveling and the greater the rate at which the fuel is being burned, the larger the force that you get. In any case, we want to try to find the velocity of the rocket. So if we multiply this equation through by dt, we get this. And so we can do the same thing to both sides. We have only quantities that involve dm, or the mass itself, on the right. The left side only depends on dv, so we can integrate both sides of the equation. We integrate the left side from the initial to the final velocity. We'll assume the rocket starts at rest just for definiteness. And then on the right side, we integrate the rocket mass from its initial to its final mass. Remember, it's expelling fuel, and so its mass is going to be going down. Two very simple integrals to evaluate, and what we end up with is this. So notice that the final velocity of the rocket doesn't depend on how you burn the fuel. It only depends on a ratio of the original mass of the rocket to the final mass of the rocket, multiplied, of course, then by the velocity of the exhaust. So just to give you an example then, if 90% of the rocket's mass, original mass, was fuel, then if you evaluate that expression, what you discover is the final velocity of the rocket will be about 2.3 times the speed of the exhaust itself. If 95% of the rocket's mass was fuel, then you could actually get up to 3 times the velocity of the exhaust. Now, one of the ideas that's being pursued these days is something called ion engines. Ion engines don't use a chemical reaction, basically a controlled explosion like in conventional rockets. They actually use a particle accelerator in order to take small bits of fuel, typically ionized atoms, accelerate them up to enormously high velocities and expel them out at those high velocities. So in that case, VE, instead of being, say, 3, 4, or 5,000 meters per second for a chemical rocket, an ion rocket can have exhaust velocities of 100,000 or 200,000 meters per second. So you can see the huge advantage in that case. Now, for those motors, the fuel is expended very, very gradually because you're only accelerating small amounts at a time. It's not a spectacular rocket burn like a typical rocket. But again, in the absence of external forces, that's okay. It may take a long time to expend all your fuel, but you can reach an enormously high velocity, much, much faster than would be possible with a conventional rocket. The other case I want to examine is what if the external force is not zero? In fact, what if the external force is just the gravitational force? So this would be like launching a rocket off the Earth. So in that case, the external force is just going to be m times g, negative because it's going to be downward. So that's going to modify our equation by just adding or subtracting an mg from the right-hand side. So then when we multiply both sides by dt, and then we can divide both sides also through by m, we get this. So now when we integrate both sides of the equation, we simply add one more integral. We're going to be integrating that last term from its initial to the final time. Just like we integrated from initial to final velocity, initial to final mass, we're going to integrate the third term, initial to final time. Super easy integral to do. It's simply going to give us one extra term. Now notice the big difference here though. The final velocity is what we get due to burning the fuel, that first term, but minus g times t. Now there's an enormous premium on burning the fuel really, really fast. The longer it takes to burn the fuel, the bigger that minus g times t term is going to be, subtracting from your final velocity. That's why when rockets are initially launched off the ground, they're such a spectacular sight. You have to burn the fuel incredibly fast. The faster you can burn the fuel, the higher the velocity you can achieve as you're trying to work against gravity, as it were. Now, of course, as the rocket gets to higher and higher altitudes, the gravitational force does actually decrease. The gravitational field gets gradually weaker. And if you're launching into orbit, instead of going straight up, directly away from the Earth, you actually start to turn and start to move around the Earth. So as you change your direction, your trajectory, then gravity becomes more a matter of turning you. It becomes more and more perpendicular to your motion, less and less parallel to the motion, and so it doesn't slow you down as much. It does more turning as you head toward orbit. But certainly in those first few seconds, first few minutes after takeoff, where you're going nearly straight up, you're fighting directly against gravity, and so you have to consume fuel incredibly fast in order to achieve a fast enough velocity.